Xin mời you can use a headphone. Yeah. Kính thưa các vị đại biểu khách quý, trong thời gian vừa qua, Đảng và Chính phủ đã ban hành rất nhiều chính sách nhằm thúc đẩy sự phát triển toàn diện của giáo dục đại học, đặc biệt là hội nhập quốc tế và đổi mới sáng tạo. Ngày 22 tháng 8 năm 2025, Bộ Chính trị đã ban hành nghị quyết 71 về đột phá phát triển giáo dục đào tạo, trong đó nhấn mạnh mục tiêu thu hút các học giả quốc tế đến Việt Nam làm việc, giảng dạy và nghiên cứu. Thực hiện chủ trương này, Đại học Quốc gia Hà Nội đã tích cực triển khai các hoạt động hợp tác quốc tế và kết nối các chuyên gia có uy tín cao trên thế giới. Trong đó nổi bật là việc mời giáo sư Alexei Ostinov, giám đốc phòng thí nghiệm công nghệ lượng tử siêu dẫn trường Đại học Khoa học và Công nghệ Quốc gia Misis Liên bang Nga, đồng thời là nhà nghiên cứu tại Viện Công nghệ Kassel của Cộng hòa Liên bang Đức, về đảm nhiệm là vai trò là viện trưởng danh dự Viện Công nghệ lượng tử trực thuộc Công viên Công nghệ cao và đổi mới sáng tạo của Đại học Quốc gia Hà Nội. Kính thưa quý vị, công nghệ lượng tử đã mở ra một kỷ nguyên mới trong lịch sử phát triển khoa học công nghệ. Những đột phá trong máy tính lượng tử, vật liệu siêu dẫn, cảm biến lượng tử và trí tuệ nhân tạo lượng tử đang được kỳ vọng sẽ tạo ra bước ngoặt toàn cầu về công nghệ, về quốc phòng, y học và trong nhiều lĩnh vực khác. Đặc biệt, giải Nobel vật lý năm nay, năm 2025 vừa qua đã được trao cho 3 nhà khoa học người Mỹ trong lĩnh vực này, lĩnh vực công nghệ lượng tử. Trong đó thì có nhóm nghiên cứu mà giáo sư Alexei Ostinov cũng đang hợp tác và đồng hành cùng. Và bắt nhịp với xu thế toàn cầu, ngày hôm nay Đại học Quốc gia Hà Nội tổ chức hội thảo khoa học gặp gỡ Hà Nội về công nghệ lượng tử lần thứ nhất. Đây là một sự kiện quan trọng nhằm thúc đẩy kết nối trao đổi học thuật và định hướng chiến lược phát triển lĩnh vực công nghệ lượng tử tại Việt Nam. Hội thảo rất hân hạnh có sự tham dự và trình bày của giáo sư Alexei Ostinov, giám đốc phòng thí nghiệm công nghệ lượng tử siêu dẫn trường Đại học Khoa học và Công nghệ Quốc gia Liên bang Nga, và giáo sư Natalia Maliva, giám đốc trung tâm thiết kế lượng tử trường Đại học Misis của Liên bang Nga. Chúng ta cùng vỗ tay để chào mừng hai giáo sư ngày hôm nay. Và sự kiện cũng là dịp để các nhà khoa học, các giảng viên, các nghiên cứu sinh, sinh viên và doanh nghiệp công nghệ cùng nhau trao đổi học thuật, cập nhật xu hướng công nghệ lượng tử toàn cầu, đặc biệt là chia sẻ kinh nghiệm phát triển hệ sinh thái lượng tử tại Liên bang Nga, từ đó mở ra định hướng phát triển nghiên cứu, chuyển giao công nghệ và đào tạo nguồn nhân lực chất lượng cao tại Việt Nam. Kính thưa quý vị, tới tham dự hội thảo, ban tổ chức xin được trân trọng giới thiệu sự hiện diện của các quý vị đại biểu về phía các cơ quan bộ ngành trung ương. Xin được trân trọng giới thiệu đồng chí Nguyễn Huy Dũng, ủy viên chuyên trách Ban chỉ đạo Trung ương về phát triển khoa học công nghệ và đổi mới sáng tạo và chuyển đổi số. Xin được trân trọng giới thiệu tiến sĩ Nguyễn Quốc Toàn, viện trưởng Viện Khoa học và Công nghệ Mật mã. Xin được trân trọng giới thiệu giáo sư tiến sĩ Nguyễn Thanh Tùng, viện trưởng Viện Khoa học vật liệu, Viện Hàn Lâm Khoa học Công nghệ Việt Nam. Xin được trân trọng giới thiệu phó giáo sư tiến sĩ Nguyễn Mạnh Thắng, tổng biên tập tạp chí Khoa học và Công nghệ Quân sự Bộ Quốc phòng. Xin được trân trọng giới thiệu phó sư tiến sĩ Lê Minh Hà, giám đốc Viện Nghiên cứu cao cấp về toán của Bộ Giáo dục Đào tạo. Vâng, về phía Đại học Quốc gia Hà Nội, ban tổ chức xin được trân trọng giới thiệu phó giáo sư tiến sĩ Nguyễn Hoàng Hải, phó giám đốc Đại học Quốc gia Hà Nội. Xin được trân trọng giới thiệu phó giáo sư tiến sĩ Trương Ngọc Kiểm, giám đốc Công viên Công nghệ cao và đổi mới sáng tạo. Xin được trân trọng giới thiệu tiến sĩ Nguyễn Trung Hiền, phó trưởng ban hợp tác và phát triển Đại học Quốc gia Hà Nội. Xin được trân trọng giới thiệu tiến sĩ Nguyễn Quốc Hưng, viện trưởng về công nghệ lượng tử. Vâng, và hôm nay cũng có rất nhiều các nhà khoa học, các chuyên gia của Việt Nam cũng như của Đại học Quốc gia Hà Nội cũng như ở ngoài Đại học Quốc gia Hà Nội đã tham dự chương trình rất ý nghĩa ngày hôm nay. Một lần nữa thì sau đây tôi xin được trân trọng cảm ơn hai giáo sư đã tới hội nghị ngày hôm nay. Và sau đây thì chúng tôi cũng xin được trân trọng kính mời phó giáo sư tiến sĩ Nguyễn Hoàng Hải, phó giám đốc Đại học Quốc gia Hà Nội sẽ có một đôi lời phát biểu để khai mạc cho chương trình của chúng ta. Xin trân trọng kính mời thầy ạ.
Kính thưa ông Nguyễn Trung Dũng, giáo sư Ustinov và giáo sư Maleva, kính thưa toàn thể các quý vị đại biểu, các thầy cô và các em sinh viên. Hôm nay chúng ta tổ chức cái hội thảo khoa học, chắc là đây là một cái hội thảo lần lượt về công nghệ lượng tử lần thứ nhất mà do Đại học Quốc gia Hà Nội chúng ta tổ chức. Thì chúng ta đều biết rằng là bắt đầu từ cái nghị quyết 57 và nghị quyết 71 liên quan đến khoa học công nghệ và cái phát triển các đại học, trong đó có Đại học Quốc gia Hà Nội. Thì ở trong đó cái công nghệ lượng tử đấy là một cái lĩnh vực mới và được Đảng và Nhà nước ưu tiên. Thì có thể nói rằng là cái nghiên cứu về lượng tử ở Việt Nam cũng như ở Đại học Quốc gia Hà Nội khá là nhiều, khá là lâu rồi. Nhưng chúng ta nghiên cứu về vật lý, tính chất vật lý của vật chất, của ánh sáng, của năng lượng, chứ chúng ta chưa quan tâm nhiều đến cái công nghệ lượng tử. Nó là sử dụng một số những cái tính chất của lượng tử của thế giới vi mô để áp dụng cho cái công nghệ mới trong tính toán, trong truyền tải viễn thông và đo lường. Thì gần đây, thì cũng phải gần đây, cách đây khoảng từ khi anh Nguyễn Quốc Hưng về Đại học Quốc gia Hà Nội thì chúng ta bắt đầu đã có những người đầu tiên nghiên cứu về vấn đề này. Và cũng rất là may khi mà có một cái chủ trương của Đảng, của Chính phủ liên quan đến phát triển công nghệ lượng tử, thì chúng ta cũng có người biết về việc này trước, và do đó là cũng là cái nền tảng để chúng ta xây dựng một cái đội ngũ để phát triển cái công nghệ lượng tử này. Nhưng mà đi một mình thì chắc chắn là không được, và với cả cái điều kiện về cơ sở vật chất con người. Do đó cái việc mà chúng ta đứng ra tổ chức cái hội thảo về công nghệ lượng tử thì rất là quan trọng. Do đó tôi rất mong rằng là trong cái hội thảo ngày hôm nay thì có khá nhiều các nhà chuyên gia sẽ trình bày, đặc biệt đó là hai cái chuyên gia đến từ Nga. Thì tôi rất mong rằng là chúng ta trao đổi để có thể làm rõ được những cái vấn đề sau. Thứ nhất là đối với cả cái bối cảnh Việt Nam, chắc chắn sẽ có một cái bài nào đó giới thiệu về cái năng lực nghiên cứu. Chắc là trong mấy hôm vừa rồi thì chúng ta đã biết được cái năng lực nghiên cứu từ đội ngũ con người cho đến cơ sở vật chất của Đại học Quốc gia cũng như là ở Việt Nam nói chung. Thì với cái điều kiện đấy thì chúng ta sẽ phát triển cái công nghệ lượng tử như thế nào? Để chúng ta đều biết công nghệ lượng tử thì nó chỉ là một cái công nghệ tiềm năng, chứ chưa phải là một cái thứ nó có thể hiển thị ra một cái mang lại cái giá trị vật chất cụ thể. Thì với cả những tiềm năng thì chúng ta cũng nên đầu tư, và tôi nghĩ rằng là cũng nên phát triển, bởi nếu mà nó thành công thì chúng ta sẽ không bị bỏ lỡ, không bị bỏ lại ở phía sau quá xa. Thế thì với cả cái mong muốn như vậy thì chúng ta sẽ đầu tư cái gì, đào tạo con người như thế nào, và cái phát triển nhóm nghiên cứu, hướng nghiên cứu. Và đặc biệt ở đây thì có anh Dũng là cái trong ban chỉ đạo về cái việc này, thì là cần cái đề xuất gì đối với cấp Đại học Quốc gia, cấp chính phủ và Đảng và Nhà nước, thì chúng ta phải có những cái đề xuất khá là cụ thể để làm như vậy. Và tôi rất mong rằng là trong cái hội thảo ngày hôm nay thì tôi nghĩ rằng là nếu mà cái công nghệ lượng tử thì nó phải gắn với cả những cái nền tảng phát triển về cơ học lượng tử, tính toán lượng tử hiện nay đang có, không phải trên thế giới và ở Việt Nam. Thì đối với cả cái công nghệ lượng tử bình thường, với cả gọi là cơ học lượng tử bình thường, cũng như thậm chí cả lý thuyết trường lượng tử, thì chúng tôi cũng có khá nhiều cái nhà khoa học mà trong nước ngoài nước mà đã từng tốt nghiệp Đại học Quốc gia, cựu sinh viên Đại học Quốc gia và cũng sẵn sàng phối hợp. Thì tôi nghĩ rằng là những cái nền tảng đã có sẵn. Thì ra là nếu mà chúng ta dựa trên những cái nền tảng như vậy để phát triển lên, thì tôi rất mong rằng là chúng ta tin tưởng hơn về cái chuyện là chúng ta phát triển cái tính toán lượng tử trong tương lai. Thì hôm nay thì chúng ta sẽ tiện được tôi nhân tiện đây cũng giới thiệu qua hai cái vị khách mời đến từ Nga. Đó là giáo sư Ustinov, là một trong những cái học giả hàng đầu về thế giới trong lĩnh vực mạch lượng tử siêu dẫn. Thì chúng ta biết là giải Nobel năm nay thì mặc dù không nói về giải Nobel trao cho công nghệ lượng tử, thì ở trong nhóm chúng tôi thì trao đổi việc này khá là nhiều. Họ cũng cẩn thận, họ nói rằng là trao cho cái gọi là hiện tượng lượng tử vĩ mô. Đấy. Nhưng mà chúng ta cũng đều ngầm hiểu đằng sau là nó chính là cho cái công nghệ lượng tử. Người đã có nhiều công trình đặt nền móng cho sự phát triển của máy tính lượng tử hiện đại. Không chỉ nhà nghiên cứu xuất sắc, ông còn là cầu nối giữa cộng đồng khoa học quốc tế, góp phần gắn kết trung tâm nghiên cứu của Nga, Đức và châu Á. Thì tôi hy vọng rằng là sau cái buổi ngày hôm nay thì có cả Việt Nam nữa. Thứ hai, đó là giáo sư Malaeva, là đại diện cho cái thế hệ khoa học trẻ có nhiều cái đóng góp quan trọng trong nghiên cứu thiết kế và tối ưu hóa bộ xử lý lượng tử, góp phần mở ra những hướng ứng dụng mới trong cảm biến và truyền thông lượng tử. Sự có mặt của hai người ngày hôm nay không chỉ mang lại ý nghĩa học thuật mà còn là biểu tượng cho tình hữu nghị với hợp tác giữa Việt Nam và Nga. Và đặc biệt đó là qua cầu nối này chúng ta có thể mong rằng là có những hợp tác với cả những nước phát triển khác trên thế giới. Xin cảm ơn sự có mặt của hai giáo sư và xin chúc cho cái hội thảo của chúng ta thành công tốt đẹp. Xin cảm ơn các vị.
Vâng, xin được trân trọng cảm ơn phát biểu của thầy phó giám đốc Đại học Quốc gia Hà Nội Nguyễn Hoàng Hải. Vâng, kính thưa thầy cô, kính thưa quý vị, bây giờ thì chúng tôi xin được trân trọng kính mời Các thầy cô sẽ cùng đến bắt đầu chương trình ngay với chuyên đề chuyên đề đầu tiên của chương trình hôm nay. Xin được trân trọng giới thiệu, chúng ta sẽ có một bài phát biểu của một giáo sư đến từ Thái Lan, trường đại học Mahidol. Xin được trân trọng kính mời giáo sư Araya Janstasti sẽ có một cái bài giới thiệu ngày hôm nay. Xin được trân trọng kính mời giáo sư ạ. Ở đây chúng ta cùng đổ chạm vào tay để cùng chào đón giáo sư.
Hello. Can you start from the first slide somewhere? This is not the first one. Okay. All right. Thank you. So this is going to be a really short. Well, it was a short notice. I did not plan for this, but since I joined the conference at Fenega 2 days ago, and so it's just like I want to explore the community of quantum research in Vietnam. And today I'm from Thailand, and I want to share my kind of experience in building the research community in Vietnam. So next slide, please. Yeah. Okay. So just a little bit of background. Since you guys are like building the ecosystem of quantum technology, I think you probably know what quantum technology is. Right now, I'm not going to go into detail of what it is, but then you know that all of like monies and startup companies are building around the world. And then what about Thailand? And what about Vietnam? What we should do? So a little bit of background about Thailand is that because we have a scholarship that we send a student overseas to study. So in the past 5 and 10 years, we have a lot of scholars coming back to the country to serve, to be the faculties and to be the researcher. And so like some of them, actually many of them are working on like quantum computing, metrology and communication. So like many of us try to like stick together and then try to see what we should do. How can we tell the government to try to like fund us to do research and to maybe like catch up in this kind of research with other countries. So we work together. Next slide. So we worked together when I went back to Thailand. So I'm actually graduate from the US, and then I worked in Australia for like a few years, and then I went back to Thailand. And my first question was like, what should I do? Like, there's no one working on quantum computing at that time. So I start connecting with people, start organizing a lot of talks and conference. And then like also the public engagement, which is like really important. You need to tell the students and you need to tell the public audience to be able to like know or realize that why quantum technology is important. And so we do these all together. And then the next slide. So we start to like build from like 20 people up to right now it's like 100 people together, like including faculties and researchers and scientists around the country. And so we start building a strong community, and we also work with the government agency. And then the next slide. And we start collecting people in the countries. So these are the organizations in Thailand, and many of them are university, and then some of them like QTFT and EQ Tech at the bottom. That is the startup companies. So we finally realized, so we worked together and we write a proposal to kind of like plan as a roadmap of what kind of things that we want to achieve in Thailand. So we end up getting the funding. So the next slide, 4, 5 to 7 years. So the numbers are a little bit all over the place. But so the thing is, right now we have like around 100 of people working in the field. We have got 9 million USD funding from the government in the past 3 years. So we start building the community, and then we start also have like the startup companies, and then like students all working together, and then also the publications in many different journals. Next slide. Okay, so in our, I'm gonna go into detail of what we are doing. So we are doing like 3 pillars. So this is the university in Thailand. So we start from the top, the university in the north. They're doing the neutral atoms, and then there will be like university in the middle in Bangkok that doing the trap ion. And also we have the south part of Thailand working on entangled photons and different like QKD system. So next slide. So we have like we divided into 3 pillars. What is the 3 pillars here? First of all, is a quantum metrology. The second one is quantum communication, and then the third one is the quantum simulation and algorithm. Okay, so the first one, so we have the lab, which is the ion trap. So I think many of you know the atomic clock. So right now the clock is actually precise, and we can use the GPS because of the atomic clock. So we have the 2 cesium atomic clock, and then 1 hydrogen maser. And then right now we are building the new kind of technology, which is like based on the ytterbium ion, which is like considered is going to be the new type of atomic clock that is more refined and like really precise. So this one we are building from scratch. So that's a picture of the cavity or the vacuum chamber, and then you have the ion trap inside. Next slide. So another example experiment is the NV sensor. So this one is a different type of sensor. So the sensor is made by the nitrogen inside the diamond. So this is like a diamond lattice, and then with the nitrogen inside the diamond lattice, it can work as a qubit, and so it can work as a sensor. So this type of sensor can be useful for like medical science or like electric field and magnetic field sensor as well. So we also have the NV sensor in Thailand, and then this one is just the data. So the current status is right now we have the plate of diamond, and we can probe the NV sensor and to be able to control like the qubit in there. So the next slide. So the second pillar, so the previous one was related to the measurement and metrology. So the next one is related to communication. So we have the lab in Thailand that also work on the development of photonic quantum gates. So there are different kinds of quantum computer in like nowadays, and one type of computer is related to the photons. You can use photons to communicate far away from each other, and then make it as like a network of computing or a network of computers. And in order to do the network, so you can use the photon. So in this case, if many people know, it is related to the quantum repeater. So in order to like make the entanglement between photon here and there, or maybe like in the north part of Vietnam, you can use photon. And you can use entangled photon so that you can do quantum computing on it. So we have the lab that works on the photonic quantum gate. We have the lab that also work on the quantum random generation. And this is the hope. So our hope is to be able to do the QKD, which is the kind of the quantum key distribution, which is like the secure communication between like 2 different places that is more secure than the RSA system that we are using right now. So actually China is actually one of the leading player in QKD with a satellite. So we are hoping to do the QKD via the satellite in Thailand as well. So the next slide. So okay, this picture is a bit off, but anyway, so the third pillar is related to the simulation and algorithm. So this is like more like a computing thing. So actually there was going to be this picture on the left, but the experiment is with the neutral atom. So we have the neutral atom, which is the rubidium type of atom, and then we put the atoms in the lattice, and then we can control each atom, and so that we can do the computation on it. So this is on the Chiang Mai University in the north part of Thailand. What they're doing is they have the vacuum chamber, and this is the picture of showing like the cloud of rubidium atom that they can trap. So the next stage that they're doing is using the laser pulse to be able to create a lattice that can trap each of the rubidium atom. So that's kind of the stage that we are on right now. Next slide. And the one that I have been telling you was like more the experimental part. There are some of the algorithm part, and actually I know that some of you are actually working on the quantum algorithm as well. So we also have the people working on like actually this quantum machine learning. So with the trying to find how to build a circuit to be able to do the neural network. Actually, you know the AI and machine learning, and this is like the next level from there. To use the quantum properties to enhance the quality of the machine learning. Next slide. Okay, so it's all over the place. So this one is actually my work. So I'm a theorist. This is part of like me working as a theorist, but also working with experimentalists to try to understand how we can like build the device that can be clean and like no noise, like correcting the error as much as we can. So as you probably know that the device that we have right now in all like the whole world is noisy, and it's not going to be a perfect computer yet. So the thing is, the theory and experiment should have to work together to find a way to correct the noise, and then how can we build like a better qubit in the future. So that's kind of my work. Next slide. So this is the lab in my university. This is like kind of the rough idea of what we are doing. So we worked on like quantum communication. We have the QKD lab at Mahidol, and we have a few people working on the BQE. Yes, and then I am myself working with the superconducting qubit people, trying to understand what kind of measurement or the error correction that we can use to improve the type of qubit, which is like actually the one that got the Nobel Prize last week. And I also working on like quantum dots, materials, and different things like quantum thermodynamics, and also like quantum stochastic process. Okay, so this is my expertise, would be more like a theory related to quantum measurement theory, and try to understand how we can measure the atom or looking at the atom, and then how to read the signal, and then how to translate the signal from the experiment. And then also, if you can look at this picture, it's more like if you have the qubits that you want to protect from the noise, how we're gonna protect this qubit from the noise in the environment, and then improve the quality of the qubit. The next one. So I want to bring it back to, okay, what's happening in Thailand? But what's the next stage? If you know that people in Europe, for example, they work together, people in Russia and like different countries in that area, they work together. And so we are here, I'm here in Thailand. So how am I gonna like build a community, right? Because I don't want to be alone. I want to work with like different countries all around. And then what I found in the past year is that there are like many communities that has been built in the past. Actually, so here is a VN Quantum, which is just started. So my QI is from Malaysia. This one is Quantum Computing Society in Philippines. And this one is from Singapore. Singapore is quite big already. BrainQ is from Indonesia. So actually, we quite have a lot of people in the area that work in quantum computing and quantum technology. So next slide. So we start building events together. We start with the Siam Quantum Science and Technology. So this is the event that I organized mainly. It was a really successful event that many people from around the world joined Thailand and enjoy the beach in Thailand. Well, Vietnam has a lot of beaches, and I'm pretty sure that many people want to come to Vietnam to like discuss quantum science. So we managed to bring a lot of scientists in quantum metrology and computing and communication to work together with us. And we have actually, it's like unfortunate that at that time I did not know anyone from Vietnam, so I did not invite you guys yet. But next time. So we have a few people from Malaysia and Indonesia as well. Next slide. Yeah. Okay, so and then later on we had the organization of conference in Philippines. So Philippines just started the first conference in KISCON in July this year. So we start collecting people from Malaysia and Philippines. They also invite a lot of industry. So Philippines has a strong point in that they have a lot of connection with the quantum computing society in the world. So they have like Continuum, IBM, and Google joining the conference. So it's just like really nice. The next one. Okay, so this one is a really nice event that we finally had the Vietnamese and Hung actually sent us like some student joining. So it was the Southeast Asia Quantathon. It's a hackathon on quantum computing. So we had like 300 applications from different countries, including Vietnam, Indonesia, Malaysia, Philippines, and Singapore. And so we like trained the 300 participants into 50, and then so they came to Bangkok last August. And okay, so the next year, 2026, next year, Vietnam is going to be the host for the Sea Hackathon. And then actually Hung and many people here is going to be the host of this event. Next slide. Okay, and this one is, yes, it just happened last month, right? That Q-Trip, or actually from the community in Thailand, we had the signed MOU to start working together with VN Quantum, and then hopefully we will have the event from there. Next slide. And then, yes, this is the event that I just joined 2 days ago. So I am glad to see that there are things happening in Vietnam, and I am glad to see that like a couple of people working on like different things that are kind of similar on the same field. So it's nice. Next one. Okay. So I want to kind of announce that like there's gonna be another Quantum Summit, the ASEAN Quantum Summit in December this year in Malaysia. So I hope that many of you guys might be able to join. So it's already announced that it's gonna be organized in Johor, which is like the town right next to Singapore. And I think the event would be like to bring the ASEAN government people together to maybe like see what we should do forward. And then maybe like sign the MOU or try to plan things ahead from there. Okay, so I think I will finish with this slide, and I put this figure as an EU quantum community, and this is like kind of the imagination. I don't know whether it's gonna be possible, but maybe it's possible in the future that in our region, at least in ASEAN region and maybe in Asia, like China and also Korea and Japan, can work together and then build a community around the area, having different meetings around, and so we can start to like work together and then build a stronger community from there. Thank you very much.
Vâng, xin trân trọng cảm ơn giáo sư. Vâng, kính thưa các quý thầy cô, kính thưa quý vị đại biểu, sau đây chúng ta sẽ cùng đến với chuyên đề thứ hai, phần nói chuyện rất là thú vị đến từ giáo sư Alexei Ustinov. Chúng ta sẽ cùng chào mừng giáo sư với chuyên đề thứ hai với tiêu đề là mạch lượng tử siêu dẫn từ tính toán đến cảm biến và truyền thông lượng tử. Chúng ta xin rất kính mời giáo sư ạ.
Ladies and gentlemen, good morning. Thank you for coming to this meeting. First, I would like to express my appreciation of being invited here together with my colleague Natalia Maleva to have this first meeting on quantum technology here in Vietnam. Well, I'm representing the Russian University, National University of Science and Technology, but at the same time I'm also affiliated with the Karlsruhe Institute of Technology in Germany, and in Russia with the Russian Quantum Center. Next slide, please. So, my idea actually is not really to spread too broadly about quantum sensing and communication, but rather focus my presentation today on quantum computing. We already heard in the previous excellent talk the other two fields. I think this would be probably more interesting if I speak actually about my field of expertise. Please. I can do this. Yeah. Show this, please. Doesn't work. Did you change your? So, I trust that many of you know about quantum computing, but just to get started, I want to say very simple words about what actually quantum computing is about. So in a classical computer, we have bits which are represented by 0 and 1. One can think of this as a particle which is being located in one well or in the other well. In this case we call it 0, in this case we call it 1. In quantum computing, what we imagine would be a similar type of arrangement, but now the particle will be simultaneously present in the left well and right well. So it will be coupled by quantum superposition due to tunneling of the wave function of the particle through the barrier. In this case, you will have two states. One of the state will be symmetric superposition of the state of 0 and 1. The other one will be antisymmetric. And then you have those two states. You could quantum mechanically describe them as a superposition of the 0 and 1, and represent this on the Bloch sphere. So this is the starting point for the imaginary quantum computer. Now, as you have already heard in the previous talks, there are different platforms to perform quantum computing, and this field has been rapidly developing over the last, let's say, 20 plus years. So, in Russia, we have the Russian roadmap for quantum computing, led by the state corporation Rosatom, and we have in this roadmap the platforms like photons, atoms, and ions being present. Also, semiconductors are being added recently, and of course, superconductors. So one can actually use different physical hardware to perform this quantum computing type quantum manipulation and information processing. And it ranges from microscopic objects like photons, atoms, and ions to more microscopic objects, as, for example, semiconductor quantum dots and superconducting quantum circuits. Can you please show the next slide? This doesn't work. No, it doesn't work. Okay, it does not. Thank you. With superconducting circuits, they are based on the Josephson effect, and actually the idea is that we take an electrical circuit which is consisting of inductance and capacitance, and then we replace the inductor by a Josephson junction, which is a structure of two superconducting films separated by a thin layer of tunnel barrier, thin layer of oxide. In this case, the harmonic oscillator, which is represented here, becomes anharmonic, and therefore one can use basically the, for example, the lowest two states in this anharmonic potential as states of 0 and 1 to form a qubit, but one can also use the resources of high states if needed. In this case, one would have a qubit, which can be also used for quantum information processing. Around the world, there has been a lot of effort in the last decade to develop quantum computers based on superconductors. And needless to say, I think everybody heard of this. There have been very impressive progress reported by IBM, by Google, and also a lot of more recent work coming from China by focus on scaling up quantum processors. Of course, these processors are not fully useful, so to say. They are so-called noisy quantum processors, which have quite high error rate. However, these processors already allow for a very fundamental step forward, which was demonstrated in the previous year by Google, which I'll mention shortly. Now, the reason for the noises in these quantum processors is due to the microscopic defects in these superconducting circuits. So if you have a qubit in any system, then this qubit is coupled to the environment. And this environment is not really fully controlled, so this leads to some random fluctuations of the fields, which modify the energy potential of the qubit. That means that this energy level separation fluctuates in time, and this leads to dephasing of the quantum state. So this dephasing is basically creating errors which are needed to be corrected. The story of superconducting qubits started about 25 years ago, and the progress has been very impressive. So starting from the first demonstration of a superconducting qubit back in 1999, where the coherence time was in the range of about a nanosecond, there have been step-by-step improvements in the coherence of superconducting quantum bits. And actually, initially the progress was almost exponential. You see this is a logarithmic scale of the lifetime of the qubit, ranging from a nanosecond to a millisecond here. However, in the last years, the kind of exponential growth of the coherence, which was over almost 6 orders of magnitude in time, from nanoseconds to milliseconds, it came to some limit. And this limit is due to the material defects in superconducting qubits in quantum circuits. So basically, the material defects, they couple to the degree of freedom of electrical circuit, and they generate this dephasing, which I mentioned. So not only the energy relaxation, which is characterized by time t1, but also dephasing is also very important for operation of these quantum bits. Now, these defects have been studied in my group quite extensively, and they are located inside the tunnel barrier of the junction, but also on the surface of the junction. Microscopic defects are individual atoms or groups of atoms which can tunnel between two neighboring locations. I'm coming to this model shortly, but want to mention that these defects are present in many physical systems. For example, they are present in non-mechanical resonators. They're even present in optical cavities, in LIGO interferometer, which has been used for detection of gravitational waves. So the accuracy or the precision of this interferometer is actually limited by defects on the mirrors, which are reflecting the laser light, which are covered by the oxide of the material. They are also present in systems and influence, for example, ion traps, due to the small modification of electric field due to fluctuations of these microscopic defects, and even in the large cavity accelerators, where they limit the quality factor of the resonators needed to accelerate particles in these settings here. So the defects in superconducting circuits, they occur inside the Josephson junction. So these are two aluminum films separated by a thin layer of oxide, about 1 to 2 nanometers. And inside this oxide, there is an amorphous aluminum oxide, which is not stoichiometrically pure, and it's not epitaxially grown. So basically, in this layer of oxide, there is a possibility that eventually there will be an atom or an ion which can go between the two locations, itself representing a qubit. But this qubit is sort of microscopic defect which can couple to the electric field of the circuit. These defects, they can be located not only in the junction, but also on the surface of superconducting films, which form the quantum circuit. So basically, we are talking here about really interesting physical situation. We have a macroscopic degree of freedom, which actually has been chosen for Nobel Prize a week ago, detection of the macroscopic quantum tunneling and energy level separation in a circuit, which is actually the center idea of the qubits. And it couples to the microscopic degree of freedom. So it's a hybrid macroscopic, microscopic quantum system, which can be recognized in this kind of setting. So there's been a lot of work about these defects in the last years. And in my group, we were funded by Google Research, here my group in Germany, to do the studies of that. So these defects, they lead to the errors in quantum computers. And here you see the statistics of distribution of T1 time in the microprocessor. You see it really spreads over the range comparable to the magnitude of this coherence time. And similarly, the IBM processors, they also show very large fluctuations of the relaxation time T1 over many qubits. So this time is not only varies from qubit to qubit, but it also fluctuates in time. So these microscopic defects, they actually couple to other degrees of freedom, and they change their properties, their frequency, for example, eventually, and this leads to errors in the operation of the circuits. In my group, we have done systematic studies of these defects, and actually for the first time we're able to prove that these defects are really two-level systems. If you have a two-level system, which means that you have two potential wells and the tunneling between those wells, these wells can be symmetric or asymmetric. And if it's symmetric, then the frequency is minimal and is given by the delta, which is the proportional to the probability of tunneling between the two wells. Once you make the two wells asymmetric, then the frequency increases, and it goes according to this textbook formula, square root of delta square plus epsilon square, where epsilon is the symmetry parameter. So if you apply strain or electric field to this defect, then the frequency of that is changing. And we have done this looking at the frequencies of the defect detected by the qubit by applying strain to superconducting chips. And actually we're able to show that these defects, actually theoretically given by this formula, all of them obey this behavior. Of course, the distribution here is completely random, but actually this dependence of the frequency of the defect, which we measure through the relaxation over the qubit, this frequency of this defect is actually depending on strain, exactly like the textbook formula gives us the prediction for the behavior of the two-level system. So the detection here is constructed in the following way. The dark color is the reduced time T1, and the white color here is the high time T1. So once the defect is coupled to the qubit, then T1 drops, which means the rate, which is the inverse T1, gamma 1 is having a peak, and this actually is represented by the dark dots in this plot. So similarly, the dependence of the defect frequency on strain can be also observed in dependence on the electric field which is applied to the circuit. In this case, we add here the DC electrodes on both sides of the chip, and then we could distinguish between defects located inside the junction and the defects located on the surface. So basically, we could certify any circuit fingerprint of the errors which are induced in quantum circuits. Well, we have some statistics about the number of those defects. We found that most of them are actually located on the surfaces. There are some defects located in the technologically necessary stray junctions, which can be avoided, and only a small fraction of those defects are located inside the tunnel junction of the qubit. So all that has been really recognized as important knowledge for improving the quality of quantum circuits. And until now, this problem is not fully solved. So people around the world are trying to improve the technology to avoid formation of those defects. But when you make this circuit in the clean room, and you take it out to the ear and bring it to your cryostat to do the measurements, then these defects are formed on the exposed surfaces, and this is some really problem in this field that needs to be solved. Now, after this talking about the coherence, I want to go to the work we have been doing in our lab in Moscow. And before that, I want to explain to you what means actually measuring the superconducting quantum circuits. So the component of superconducting quantum processor are not just a chip. You see the chip there, and this is a small chip for a few qubits where these dots are coaxial cable connectors to provide control signals and readout signals for the circuit. This all is placed in the dilution refrigerator, which is kind of a refrigerator to leave the temperatures where the thermal fluctuation energy becomes smaller than the energy level separation between the quantum states. You have to use the electronics which is required to manipulate the qubits at the gigahertz frequency, so we have to generate pulses of a few gigahertz and duration of some nanoseconds or microsecond long. And of course, you also require a lot of electronic components. So all these things come together if you want to really develop something functioning using this technology. Now, at MISIS, we have been working on the Russian roadmap of quantum computing, which started in 2020. And the first phase of this roadmap ended in 2024. And one of our achievements, this was around 23, was a processor of 8 transpond qubits, which are shown here with control lines. And this processor actually is functioning quite reasonably well. So we have been able to implement here single qubit and 2 qubit gates using the coupler of original design, which is shown here. Basically, we have 2 qubits left and right. The qubit itself is actually not seen. It's need to be magnified if you want to see the qubit. It's like that or like that. But in between, you have a bar where I have a superconducting quantum interferometer device, basically classical but made small, which can be tuned in magnetic flux. So if you want to talk, if the qubits have to talk to each other, then this device is placed to the magnetic flux of being very high induction, inductive value, and if you want to switch it off, then this inductance is made nearly zero, and then there is a short to the ground, so the qubits don't talk to each other. And this kind of approach proved to work pretty well, so we were able to implement here 2 qubit gates with fidelity about 98% and duration about 60 nanoseconds. So this has been, of course, done by cross-entropy benchmarking, which is a standard for testing these quantum computing circuits. We have also done some work on the approach where we use high states of this qubit. And this is the work, actually, I think there also was work in here in Vietnam done on qubits, so where the more than 2 states are being used there. So here we have actually did some kind of quantum simulation using the, observing the range of the phase transition, it is symmetric phase transition. And interestingly, you see here actually 3 plots. This is the theory, this is the result obtained with supraconducting circuit, and this is the result obtained in a similar experiment with an ion with our colleagues in the neighboring group in Russia. So actually using 2 different hardware platforms, we have in both platforms good agreement with theory, thanks to the ability of reading out all 3 states in this kind of experiment. Now, our focus in the group at MISIS is actually currently to develop an alternative platform for supraconducting computing. As you know, all the groups which actually scaled the qubits up, including Google, including IBM, including China, they work on transmons, which I introduced in the previous slide. However, transmon has a disadvantage of having a relatively small unharmonicity. And that means that you cannot really execute very quick gates. Another drawback of the transmon is that you need to go up in frequency to several gigahertz, and normally you have to up-convert the frequency, which adds additional errors. If you go from transmon to a fluxonium device, then the frequency of the energy level separation in the most favorable working point becomes lower than 1 gigahertz. That means that one can actually generate the signal digitally using arbitrary waveform generator without up and down conversion, which actually reduces the experimental overhead and reduces errors. So with this approach, we have been actually competing with several other groups in the world. There are competitors now, people at MIT and at Lausanne in Europe, and the group which actually worked on that in China, the company Alibaba, which now stopped their project, but the group is there, and they're actually not far from here. They're working in their new S lab in Shenzhen. So basically we were able to show in the first steps, this was already like 3 years ago, single qubit fidelity of 3 nines and 2 qubit fidelity with 2 nines, which is that time up to the state of the art worldwide. Now we were able to also to show a new type of gates between fluxonium. In this case, you have 2 fluxonium devices on the same chip, and then you apply microwave pulses only to the coupler between the 2 qubits. And this allows to make a very quick gate with rather high fidelity, which is actually described in this paper listed below. Now, currently we are working on the project. One of the projects is developing 3 fluxonium gates. If you couple not 2 but 3 qubits together, this opens an opportunity to do interesting quantum algorithms which could be more efficient than just doing the 2 qubit gates. For example, would be a Toffoli gate, which can be done on 3 qubit, actually would be done in 1 step, and if you use 2 qubit gates, then you would require 6 of those gates to achieve the same result. So basically, you could, due to the limited coherence times of these qubits, one can actually use 3 qubit gates to have more efficient algorithms compared to the 2 qubit gates, which are the conventional computational approach. This is our chip, which is now in the lab, and the measurements are being done. So this is a real device actually now, which is being measured these days. Now we have established at MISIS a fabrication of supraconducting qubits with reasonably high T1 and T2. These are examples of our circuits. We collaborate with the Institute of Nano and Microelectronics of the Russian Academy of Sciences, which is rather important for this collaboration. So this is our achievements by the end of last year. Beyond the 8-qubit processor, we developed now 16-qubit processor with 2-qubit gate fidelity about 98%. We also developed the 3-qubit CCZ gate, which I mentioned, with fidelity about 95%. And actually, we started working on the error correction. Error correction is a very important step in quantum processors because, as I said, these processors are noisy, and without correcting for errors, the benefit of quantum computation is very limited. So one actually has to sort of find a way to avoid errors, either completely to make it fully correctable, or at least partially correctable to increase the depth of the algorithm. And the idea is that when the quantum state is being distributed over several qubits, and then the errors are being detected due to the weakness of the ancilla qubits, which are shown here in blue. And then data qubits, for example, in the 2-qubit here, they detect the same type of error which occurs in this qubit, and basically this error can be corrected without destroying the quantum state. And this is done for the Z error or for the X errors. So this is the core of the so-called surface code, which is being proposed for this planar architecture. Now there are also other approaches to that, but our approach is to use dynamically reassignable qubits. So, for example, if we want to work with 2 physical qubits, we can start with physical states of qubit 2 and 3 using an ancilla qubit, which is qubit 1. And then by doing the quantum manipulation, we could swap the state into the qubit 1 into the qubit 2, and then assigning the ancilla function to the qubit 2, and then further to qubit 3. And then these results are compared now with a conventional encoding where the qubit 2 is being used as ancilla. And as you see, the agreement and fidelity of that is being preserved. So there's basically not yet error correction, but it's error detection which is required, which is the first step for the error correction. So this has been implemented on the 8-qubit processor, which I mentioned before. Now, concerning the fluxonium gates, you see here the fidelity in percent for transpond qubits. These are the first 2 bars. And this is 3 nines, almost 4 nines for the transpond. The best transpond, which has been demonstrated in the community, reaches safely 4 nines. Now with fluxonium devices, we have already now 4 nines single qubit gates, and actually this still can be improved. That's what we're working now to reach even next step, maybe 5 nines. And the best fluxonium, which has been developed at MIT, actually reaches a bit higher. So this number is now being achieved. So basically fluxonium devices, as you see here, the last 2 bar, they overcome the transpond devices. And this is quite encouraging to think about developing an alternative platform. And this is the situation in this field. So, you know, many groups, they went to the standard route of developing transponds because it's easy to make and you can scale up, and people have done this, you know how to repeat this. And many groups in the world actually just followed this mainstream. However, I think the game is not over, and there are other superconducting circuits, alternative circuits, as for example fluxonium, which can be used for much more efficient and more precise quantum information processing. And this is currently being still an open question. So I would say for the newcomers in the field, one should not be afraid of trying something different from the mainstream, which has been explored by world leaders or technological companies which have been in the field for a long time. So one should be able actually to find our own path and explore it, and maybe have a chance to overcome on the turn the progress of this technology. So this is a picture of our lab at MISIS. We have currently 3 dilution cryostats, and actually getting 2 more dilution cryostats installed now in October. We collaborate with several other groups in Moscow, And in our group at VCs, we started in a situation maybe a little bit similar to the situation here. There was nothing in Russia until about qubits until 2011, and we started building a lab at VCs about that time, and we were about 25 people on the year 2020. From that on, there was a development of the Russian roadmap where we took the commitment to scale up our 2-qubit transfer processor at that time. We scaled it now in 5 years to 16 qubits, and 16 qubit and 18 qubit circuit have been demonstrated. And we took a decision actually to switch over from transmons of Watsonium because reaching the leaders with transmon technology makes you just repeat what other people have done, and I think it's really important to have the expertise to do something new, to do some to implement some ideas which have not been done by other people. So we established a new fabrication track together with the Institute of Nano and Microelectronics, and as you see, the team has grown by more than a factor of 2. I would like to close my presentation mentioning this Nobel Prize, which actually I gave a public lecture 2 days ago here in Vietnam. And yeah, I had the privilege to know all these people rather close and have some joint papers, both with John Martinez and John Clark. And this is the discovery which was made pretty exactly 40 years ago, where these people were able to demonstrate macroscopic quantum tunneling, which I described in the beginning, tunneling between the 2 potential wells, and energy level quantization, which is essential in electric circuits, which is essential for operation of the superconducting qubits. So I think it's really exciting that in the year of 100 years of quantum mechanics, the award is given to the researchers who have been able to show that quantum mechanics is not limited to microscopic world. It actually extends to the macroscopic world, to the circuit which you would see with your naked eyes. And the key here to actually to be able to recognize this quantum dynamics in experiment, which requires, in this case of electric circuits, low temperatures. But if you look at the progress in cryogenics in the last 20 years, it's very impressive. Previously, to reach these lowest temperatures, we had to use liquid helium and even more expensive helium-3 isotope to go below 1 Kelvin. Nowadays, these refrigerators are massively produced by companies in Europe, US, and also now in China. There are many companies producing these dilution refrigerators, and they become cheaper. And they are actually not that costly anymore because in operation, because they don't consume liquid helium. They use closed cycle for cooling from room temperature to millikelvin temperature within a few hours. And if you look back 100 years ago, when we had, as a surprise, refrigerators in every kitchen, now, that time it was very new and cost very much money. So once the massive production started, nobody's surprised of having a refrigerator in the kitchen, which goes, of course, not that low. But with this new technology, I think the demand of having refrigeration to lower and lower temperatures is there, and obviously this technology becomes more affordable for the whole world. So this is not the end of the game. There is also an opportunity to increase the frequency of superconducting qubits. There is a room above that. In this case, one can go up in temperature to maybe just conventional helium temperature, which makes the operation even simpler. So I think we shouldn't be scared that superconducting qubits require low temperature. This is doable and affordable, and there is a technology, cryogenic technology, to do that. So with that, I would like to thank you for your attention and
Vâng, xin được trân trọng cảm ơn quý vị đã lắng nghe bài giới thiệu của giáo sư Ustinov. Và vừa rồi thì vừa rồi chúng ta được nghe được hai bài thuyết trình của hai giáo sư, một giáo sư đến từ trường đại học Magidon và giáo sư Osinov, và ngay bây giờ thì chúng ta sẽ cùng đến với phần Q&A. Có lẽ là hôm nay có các thầy cô ở đây cùng rất nhiều các sinh viên, và xin mời các thầy cô và sinh viên, những nhà khoa học có thể đặt những câu hỏi cho hai giáo sư người nước ngoài, một giáo sư đến từ đại học Magidon và giáo sư Osinov trong buổi hội thảo ngày hôm nay ạ. Xin mời các thầy cô có chia sẻ gì không? Nhất các bạn hôm nay có các bạn sinh viên, và xin mời tiến sĩ Cương Hưng ạ.
Maybe I can ask you in English. So you see, you have a very nice SEM picture of the qubit with coupling and fabrication, and also even the all the coupler and stuff like that. Why should you make the chip? Can you do all the overedge and all the in pieces?
Thanks for the question. So we do all the thin film deposition and film processing at MISIS, but we collaborate with people who are specialists in e-beam lithography, which is actually an institution not far from MISIS. It's only like half an hour travel by public transport. And this actually is important because for not a big lab, developing all the resources in one place is quite costly, and you also need to train the people to do this. And we found that actually this kind of academic outsourcing is extremely effective and beneficial for all sides. So I think this, in this case sense, cooperation between different specializations is very important. So we almost do everything in MISIS, but with the help of e-beam lithography of the place where they could do it professionally better than we could. Thank you.
Vâng, xin cảm ơn giáo sư ạ. Xin mời các câu hỏi khác. Vâng, xin mời anh Toàn.
Yeah, thank you very much for the nice talks. I just want to ask about the overview of the development of quantum computing in Russia. If you could have I'm the faculty of physics. I try to formulate in this direction. For example, for the faculty also collaborate with outside as well, and you can have advice on to focus on maybe some strategic because I guess it's need times to develop a strong research quantum groups here together with Japan and BNU. But it seems to be like we have the will, but it's still like finding out our way. So if any advice for me to the research.
Yeah, I can tell you as an example. I think the idea would be, of course, to get young people involved in this development, properly trained. And we had this situation at MISIS when we started the lab about 14 years ago. The students, they had not seen the function of the lab before. So we were simultaneously building a lab from scratch. We had generous funding from government, around $5 million to build a new lab and buy equipment. At the same time, we took several talented PhD students, and I invited them to go to Germany, which was a functioning lab where we had all those experiments already going. And they saw how things work. They realized how the team should run. They realized what is the hardware which they are going to get. So this was very efficient in a short time for them to learn by the example. So in this case, I think the exchange of people between the new laboratory which is going to be built and the laboratory which is already functioning is very efficient. So I think in this case, I think the cooperation is really the major factor. So, but of course, I mean, building up a lab in this country which can do this kind of experiments will very quickly bring young people to the level which is competitive worldwide. Because once they find the tasks which will be original and then relevant for the research in this field, then of course things develop themselves. So one has to give a small seed, and then things really fly. So that's our experience with missiles.
Vâng, xin cảm ơn giáo sư ạ. Và ban tổ chức có nhận được một câu hỏi từ một đại biểu tham dự họp online. We have questions from the online audience. Câu hỏi là you talk about gate fidelity. Can you comment on scale difficulty on just read?
Okay, the question is about the gate fidelity and difficulty in scaling. Of course, the gate fidelity depends how you operate the qubit. If you take 2 qubits and don't do anything else, just try to make a 2-qubit gate, then of course you can reach a fidelity which could be having some number and behave. But in reality, when you operate a large chip, you have to do many gates simultaneously. In this case, one has to distinguish between the mark, kind of fidelity mark, which you get for the 2 qubits individually and for the whole chip when you operate many of them simultaneously. The errors in large chips, they actually occur not only through the decoherence of individual qubits, but also through the crosstalk. And we call those errors as coherent errors. So these errors actually are not induced by defects or limiting quality of the resonators and qubits, but rather induced by the mutual parasitic interaction, which you don't want. If you want to talk to qubits A and B, you simultaneously have a small interaction with qubits C and D. So these type of errors are most difficult to suppress, and this is a relevant question. So the approaches are actually to isolate microwave lines, which requires a lot of microwave engineering, and there is a certain know-how in the field how to do it. So we are aware of this problem, and the fidelity which I quoted was the individual 2-qubit fidelity. So it will be reduced once we talk about the fidelity for the whole chip. So this relevant question and needs to be addressed.
Yeah, thank you very much, Professor. Vâng, cảm ơn giáo sư ạ. Vâng, xin mời câu hỏi tiếp theo, xin mời em. Vâng, có tiếng Việt ạ. Vâng, các bác có thể có tên Việt nghe được ạ.
Thưa giáo sư, cho tôi hỏi câu hỏi này. Có thể ứng dụng cái lĩnh vực lượng tử vào trong các vấn đề về phân tích tài chính hay không? Giả dụ là các số liệu của tài chính sau một cái quá trình mã hóa thì chúng ta sẽ đưa vào các cổng, chúng ta sẽ thiết kế các thuật điện tử và biến các cái dữ liệu đã mã hóa này thành các cái quy bit siêu dẫn, và trong đó chúng ta sẽ điều khiển các quy bit siêu dẫn và chúng ta cho vương víu vào nhau. Thì trên cơ sở đó thì chúng ta phân tích các cái vấn đề của nền kinh tế và tài chính. Thì không biết có được hay không ạ? Cái thứ nhất. Thứ hai là cái quá trình hôm nay thì phát triển toán học đang nâng cao, thì liệu có thể ứng dụng cả cái kết hợp giữa lượng tử và những cái vấn đề về toán học topo trong cái vấn đề về phân tích kinh tế tài chính không ạ? Xin hỏi giáo sư.
Well, I would like to, I mean, I cannot really probably give the full answer to this because I'm not a specialist in algorithms, but what I know about that quantum computing can be applied to different problems, including financial analysis. So one can actually use quantum computing in particular for the optimization problems. If you want, for example, to find a quick solution analyzing the market and then have a quick decision, then quantum computing basically analyzes the data simultaneously rather than doing it one by one. So this is the advantage of having this large scale, this large Hilbert space which is characterizing the quantum computing. So basically we have the opportunity to develop new algorithms. However, these algorithms require better hardware. So your question is sort of a goal which we anticipate to reach, to apply this to different applications like financial markets, optimization of the logistics, quantum chemistry to develop new materials. However, this requires high quality hardware. And this is actually the task which we are still solving. It's not yet solved. So thank you for the question. It's the future, but not yet the reality.
Thank you, Professor, for your very nice talk today. And I can see that your topic is about superconducting quantum circuits. So I have a question for you. Can you tell us about the current situation in your labs, in your university or your country? How it can apply to the quantum technologies? And the second question is that I care about how we can use this superconducting quantum circuits into our quantum technologies in some institute and university in Vietnam. Yeah. Thank you so much.
Thank you. In Russia, we have the national roadmap for quantum computing. This roadmap was started in the year 2020, and the first phase ended in the end of 2024. And now this roadmap is approved by government and is funded now for the next period of 5 years until 2030. This roadmap includes different platforms, and a superconducting platform is one of the 4 major platforms: photons, ions, and atoms, and superconducting circuits. And with superconducting circuits, we can already execute some simple algorithms. So the idea in Russia is that this quantum computing roadmap is organized by the company, which is state-owned. It's the company called Rosatom, which takes care of nuclear energy production in Russia, including various applications of nuclear energy. So they're also building, big nuclear plants around the world in different countries, and they have a knowledge about atom, which means they know what is quantum. This was the idea of the government. This company they are very big. They should organize the roadmap of quantum computing. So there are already many algorithms which are being explored, not only on our platform, but actually primarily on the ion platform, because our colleagues, the ion tracking group, they have been very quick in developing, I think they have now about 50 qubits implemented in the ion traps. And they already execute many algorithms. I think superconducting platform, which we developed, we were a bit slowed down due to the technology limitations. In the recent political situation, we could not buy new equipment, and therefore we had to sort of think what we could do different from the mainstream. But overall, I think we have done some work, for example, implementing some simple algorithms as a demonstration of the case with another state-owned company called Rosneft. It's a state oil company, where they, for example, their problem is solving the logistic. If they transport oil from one part of the country to another, the certain pump can break, and they have to find the most optimal solution for the route to of the oil to go through other pipes. So basically, this decision has to be taken quickly because it costs money. So companies like this, they have interest in using quantum computing for optimization problems. But the horizon, of course, is much farther. One can, for example, develop new materials using the quantum computation, because in this case, one does not need to use approximate methods, which are the tool in quantum chemistry. So there are many applications where one can envision quantum computing, and of course the hopes here sometimes they're flying ahead of the reality, but I think this is the technology of the future. We have to have those hopes and try to bring them closer.
Thank you so much, Professor.
Thank you, Kissinger Professor, for the insight shared earlier.
I am come from Quantum Technology Department from the Academy Military Science and Technology. So I have a small question for Professor. Aside from choosing superconducting technology, how do you evaluate ion trap technology, which is more affordable and maybe accessible option for Vietnam? Thank you.
Thank you for the question. Yeah, as I mentioned, ion trap technology in Russia has done very quick progress. Now, the problem there is that the ion trap technology, which was implemented in several groups in the US and also in Europe and in Russia now, they've been using the standard power trap, which is like you have in vacuum one-dimensional chain of ions, and then you perform quantum computing using the modes, which are the elastic oscillations of the chain. So one uses the mechanical degree of freedom to couple any qubit with any other qubit. The problem is that with this approach, the size of the system is limited. And in practice, it's limited to at maximum maybe 50 or 100 ions. And this has been recognized as a major problem. And currently, in ion technology, the progress is focused, the future is focused on developing their own chip traps. There is a company in the US, Honeywell, it was original name, they developed this technology. Well, they demonstrated very high fidelity gates. But these high fidelity gates, they achieved on small scale fractions of the chip. And if you want to use this technology to a larger scale, then the limitation of ions is that the gates, when you transport the qubit from one location of the circuit to another, ions, these gates become very slow. So this is the problem with ion technology, that it works now for 100 qubits. But how to make the next step makes it still a big issue. So clearly the competition between different platforms, ions and atoms and superconductors is worldwide there. The winner is not yet known. Currently the most investment goes into the superconductors. But yeah, remains to be seen. So we don't know the future. We'll see which platform will win.
Thank you, Professor.
Thank you, Professor. I know you are very strong in superconductor and application in quantum. So I'm interested about now many research about quantum gates use silicon base, special for quantized silicon. So I want to know and your opinion about using the silicon spin using for integrated circuits, and maybe now Vietnam very interesting in semiconductor industrial. So
thank you for the question. Well, as you probably know, the idea of Kane about using the impurity spins in silicon has been taken by a large project in Australia, and they've been developing this over a long time. And the results which were demonstrated there are like single qubit gates and more recently 2 qubit gates in the group of Andrea Marello are very impressive. However, they, to my knowledge, have not been able to move beyond 2 qubits. The problem is that one needs to locate the impurity spins very close to each other inside the isotope-free silicon, and this is technically rather difficult. One can use ion implantation, but then making the environment of those implanted ions clean is difficult. So basically they face the problem of scaling up, which requires more work, and I think they don't give up. But they have not done really much beyond 2 qubits, to my knowledge. Though the fidelity is already quite good, and the other approach in semiconductor spins will be using quantum dots. And there are different groups around the world working on that, also in Europe, and I think in the Intel is strongly interested in that. Again, they can demonstrate small processors, maybe like 5, 8 qubits. I think there's been some work on that. But scale beyond that is difficult because they require many gates. And how to bring those gates to the quantum dots, which they need to control, is topologically difficult. So this is an interesting direction because semiconductor world has been, of course, very much advanced by semiconductor technology over the last half century. But still, I think the competition, they don't really stand yet the competition with the other platforms like ions, atoms, and superconductors, where the large scale, 100 qubit scale processors have been demonstrated. This is not yet achieved by silicon technology.
Thank you, Professor, for giving out a very interesting lectures. And I was also on the public lectures the other days, and it was really bugging me that what should we do? Like, I mean our young generations, our young Vietnamese scientists. What should we do? What is our strategy? And have you got any advice for us as the young communities, the very talented one, but very limited on resources, on how to participate on these problems? Thank you very much. Spasiba.
Well, thank you for this question. I think your advantage is that you are young and curious. And the curiosity, this is the mechanism which drives science. So you have to ask questions which are difficult to answer, but then try to answer them. And this is what actually makes life interesting of a scientist. So clearly, I think there is an interest in Vietnam to start the quantum technology development, and this is very timely and very, very good. But one has to start from something not large scale. And in this case, I would advise not to hope to overcome world leaders, but rather find your own original track. And then try to do something small, step by step. Once you are in that business and already sort of can present this in the international community as your original result, then things start developing, and one has to start from something first. So hopefully there will be a new laboratory developed on the new campus of the Vietnam National University. And in this case, I think there will be experimental facilities to start doing something practical. At the same time, going abroad and learning in the already working lab, for example, Russia or Germany, which already work in the field, will make your learning curve very quick. So once you've done this, you know better what you want to do. So my advice is not to be afraid, go in the lab, make your hands dirty, and then you will have fun.
Vâng, xin cảm ơn câu trả lời rất thú vị của giáo sư. Bạn còn có câu hỏi gì nữa không? Vâng, cảm ơn bạn. Xin mời các câu hỏi tiếp theo. Có lẽ là trước khi xin lỗi anh một chút là ban tổ chức có nhận được một câu hỏi của khán giả đang dự trực tuyến thì có lẽ là xin được hỏi giáo sư luôn. I have an online question from the audience. In your opinion, given the current situation in Vietnam, how much time would we need to be able to build a quantum computer like the one in the lab? And how much investment would be needed for human resources?
Well, I mean, the numbers, financial numbers is not my specialty. Well, developing a quantum computer from scratch would not make a lot of sense. I think the meaningful development in this case, I would consider growing the expertise in the country of people and scientists who can actually know this technology, which can apply this technology. And there is the whole world of the new kind of study line, which we pursue in MISIS, is quantum engineering. So if the country wants to participate in this progress, it's not the question of building your own quantum computer only. It's the question of having the expertise of people to operate the computer and actually to understand how it works and actually benefit from that. And in this sense, quantum engineering is a discipline where there is a merge of different fields of science. One has to know quantum mechanics, which means physics. One needs to know microwave engineering, which is engineering. One needs to know also some algorithms, which is IT. So combining all this knowledge together is very crucial in order to be in the field and to be able to compete with the rest of the world and contribute to the scientific community worldwide. So I think answering the question when the computer will be available, one can actually buy a computer. Like in Germany, they bought 2 computers from one from D-Wave, the other one from IBM, and they operate those computers in Fraunhofer Institute in Stuttgart in one place and the other place is in Munich. So there is nothing wrong about trying to learn from existing computers, but it's better to have your own, which you can operate and touch and really understand how it works. Doing it just in the cloud, online, like IBM offers, is an opportunity, but this doesn't really give the full expertise to the researchers in the country. So I think learning by doing is the approach.
Thank you very much, Professor. Và có lẽ là xin được mời anh câu hỏi tiếp theo.
Professor Sino, I have 2 questions. The first one will come back to the science part. So I have a technical question about how can you determine the fidelity of the quantum gate? Can you tell us a little bit how the measure is? And the second one is for the curiosity. So I came to know about your work earlier, like 15 years ago, you worked about the superconducting metamaterial and what is the potential of the metamaterial for, how to say, to improve the limitation of the traditional conventional material, and what is the future of the superconducting metamaterial, if you can tell us. Yeah.
Thank you for the questions, interesting. So, the question about fidelity is that the standard procedure which has been introduced by Google, which people also use worldwide, is the so-called cross-entropy benchmark. That means that you select a certain group of gates, and then you execute these gates in a random fashion, and then you basically execute the gates back, and then you compare the initial state with the final state. And this gives you the fidelity basically by deviation of the initial state from the final state. So, but there are also other techniques which can be not that, let's say, consuming, like for the cubic gates, one can do it a little simpler, but this is like a more detailed story. But in principle, this is executing random gates. This is the way to determine the fidelity. The second question is interesting because our laboratory at MISIS, it was initially named as Laboratory for Supraconducting Metamaterials. And now we sort of recognize we are working already broadly in the field of quantum computing. We renamed it to the supraconducting quantum technologies. Now, supraconducting metamaterials are interesting because the metamaterial is a kind of idea that one can use a certain medium with some specific interesting properties to do something non-trivial with electromagnetic waves, with light, for example. But for us, light is microwave. So, and supraconducting metamaterials, they allow to have frequency tunability. They allow to have very, very low loss and also introduce nonlinearity. So, in principle, it can be used for example, very sensitive devices for amplification, for parametric amplification. Arrays of superconducting junctions can be used also for like quantum limited amplifiers, which are also needed for quantum computing for the real out. So, but I think in terms of academic interest, this is really nice and interesting. But as for the field of metamaterials, I think this community is kind of exhausted a little bit the expectations, because I think the killer application is not found yet. So they talk about the phase array antennas and things. I've been several times on these conferences, but I think there was a lot of hype back 25 years ago when they started this field. I mean, John Hendry and Smith and so forth. Yeah. But still, the killer application didn't come. And I mean, academically, superconducting metamaterials, also quantum metamaterials made of qubits, are very interesting, because one can study an ensemble of artificial atoms and study interesting physics there. But I think the application is really important for the field to stay for long. So we like it. We still do some experiments. I have a researcher who's working now on following up in this direction in Moscow lab. But it's not, for us, not mainstream, because there are other interesting things to do now.
Vâng, xin cảm ơn ạ. Và xin mời em.
Thank you, Professor. I have a question. I would like to return about quantum computer, because you know that you suggested to start on something that we need to start on something not from scratch. That means it's better to buy a computer, quantum computer to test on. And could you suggest what is optimized start point, how many qubits? And because we don't not only learn from it, but we would like to do some experiment or to do some simulation on it. So what qubit is enough for start?
I would say the short answer is very few. Don't try to buy a large system with 100 qubits, because as a car, if you get a car and you want not only to learn to drive, but you want also to understand what's inside, you need to be able to put it apart, to put it in parts and then put it back together, and then be excited that it works again. So you need something very simple, which will be maybe only a few qubits, which are already being assembled to operate. But then try to then get some your own idea, put a different chip there, and see how a different idea would work. For example, using different type of qubit, or different type of gate, or something else. So this is really the curve which is probably the most optimal. If I want to learn some programming language, as a student, I remember it was so boring to read the books about Fortran. So what I do, I just take a program which works, and then I start changing something in this program. And then it stopped working, but then I figure out what was my error, and I learn by that. So this is the quickest way, I think, to get into it. But don't get too large program with 1,000 lines of codes, because this will make it impossible to combine it back once it stops working. So better something simple, few qubits.
Thank you, Professor, for very interesting talking. I have a question. This is first, what do you think about the future of quantum computing in the next 10 years? And it's the second question. How do you think about in Vietnam? What do you think we should focus the focus in the direction in the quantum technology? Thank you.
Thank you for the question. For two questions. So about the future of quantum computing, if you want to make the God laugh, tell about your plans. Yeah? So, but in principle, I think the situation now, as I see it, is better than it was maybe 2 or 3 years ago. It was clear 2 or 3 years ago that there are large processors which have been demonstrated. But clearly, the error rate was too high to make them useful. And it was very crucial to demonstrate the error correction. Now, the error correction has been demonstrated by several groups. It's a very important result of Google of last year, I think early this year. They were able to show that increasing the size of the cluster, they can reduce the errors in their already existing circuit by increasing the size of the distance of the code. They increased from 3 to 5 to 7, and they saw the reduction of the error rate. So this is very important demonstration because this experimentally shows that error correction works. Because before it was only theory. So now I would say the future looks much better than it was 3 years ago, before this was demonstrated. But clearly, the progress will be depending what will happen in the next maybe 5 years. So I think this distant future of 10 years, I think we just need to keep going and see how far we can get. You know, this is something, you know, you dream about something, you don't think it's real, you start doing by hands. And then it works. So this is surprises which progress brings. Yeah, the second question was about, sorry.
How do you feel about Vietnam suit is the focus?
Yeah, where should you focus? I think you should focus on the direction where you have some seeds in the field. So if you have some expertise already, some scientists or some platform, for example, in superconductivity, I think you have some really excellent expert already. If you have the other platforms where you also have some knowledge in the country, where you could start from something already existing, then you develop this. And in Russia, they decided to go broad, and this was very productive because different platforms, they also learn from each other, they also compete. And there is nothing wrong in having maybe more than 1 or 2 groups working. Like in superconductivity, we have 3 groups on main qubits in Russia. So this competition is also important to broaden the knowledge and it stimulates the progress. So I think it really depends on the seeds which you have there already, and start developing this. And then don't try to develop from scratch something where you have no one knowing about it.
Vâng, xin cảm ơn ạ. Có lẽ là chúng ta cũng đã có khá nhiều câu hỏi dành cho giáo sư Alexei và sư Nút rồi. Và chúng ta sẽ còn những cái phần talk ở sau nữa. Và bây giờ đang là 10 giờ 40 thì xin phép là mời các thầy cô và các quý vị chúng ta sẽ nghỉ giải lao trong vòng 20 phút. Và chúng ta